Hi there, my name is Florian, I'm from the LMU Munich and I'm going to present to you some work that I conducted together with my co-authors Daniel, Andrii, Dominik, Sebastian, Thomas and Martin on a toe-based input modality. Over the last few years, we have seen a constant stream of works exploring food-based interaction techniques for all kinds of devices and contexts, from desktop PCs to head-mounted displays, and I have also written a couple of these. If we now take a closer look at these papers, we see that they are mainly concerned with the external degrees of freedom of our foot. That is how the joint of the knee together with the leg and also the ankle joint move and rotate the foot as a whole. What we haven't seen that much in contrast is research on the internal degrees of freedom of our feet, especially with regard to our toes. And those few papers that considered the toes for input mostly used them as simple binary switches for pressing buttons. However, if you give this a try and play with your toes, you realize that we probably can do more fine-grained operations than just pushing buttons with our toes. And this is what we are looking at in this paper. How accurately and efficiently can we use our toes for interaction, so as an input modality. Here you see an illustration of the main muscles in our feet. I'm not going into details on the exact anatomy, but one key thing that we can see here and that you can also realize when trying to move your toes is that there are muscles that allow us to flex and to extend our toes, that is moving them upward or downward. And second thing to remember, that all but the big toe are extended and flexed by the same muscles. This means that while we can independently move our big toe to some extent, independent movement of the remaining 4 toes is not feasible. Based on these two findings from the anatomy of the human foot, we designed a controlled experiment to understand the accuracy, efficiency and user experience of toe-based interaction. For this, we varied 5 independent variables. And the first one was the toes used for interaction, which we varied between the big toe, which is also named hallux in the medical literature, the remaining lateral toes and all toes together. As the foot and our toes are obviously involved in the process of keeping our balance while we are standing, we also varied the posture as a second variable between standing and sitting. Third, we varied the direction of the interaction between extension and flexion, so upward movements of the toes or downward like crabbing movements. Finally, we wanted to understand the capabilities for fine-grained interaction, so we also varied the subdivision of the interaction area as the scaling with 4, 12 and 28 subdivisions per direction. So that means in both extension and flexion direction. As well as the target with 4 levels. Through the design of the scaling and the target factors, all targets were in the center of a field of the scaling. To accurately track the participants' toe movements, we used an optical tracking system and attached reflective markers to the hallux and the third toe. We then calibrated the maximum movement range per participant and mapped our targets to this range. Now, what did we have our participants do? We placed them in front of a screen that depicted the scaling. You can see it here on the slide. And then one of the targets was highlighted in red, and the participant's first task was to move their toe to the highlighted field. You can see that the current position was highlighted in blue, and once participants reached the target, their task was to press a button that they had held in their hand. Directly after the click, you can see that the system removed all highlighting, and the participant's second task was to hold their toe steady for 3 seconds. And this is something that could be used for selection in a later system, similar to dwell-based selection in a gaze-based interaction technique. So here you see an overview of the methodology of our experiment. We had the 5 independent variables that I already talked about, and we measured these dependent variables to assess the accuracy, efficiency and user experience of our 18 participants. Now let's have a short look at the results, and just as a warning, this is a really number-heavy paper, so I only provide you with a short glimpse on the results here. For much more findings, please have a look at the paper. So the first thing that I wanted to share with you is that toe-based interaction actually works. Obviously the scaling, so the number of possible items to select, had the biggest impact on the accuracy, but with 4 targets per direction we found accuracy rates around 98–99% when using all toes together. When we increase the number of options, we obviously decrease the accuracy. So remember, toe-based interaction works, but only with a limited number of options. Another thing that showed a strong influence on the accuracy was the selection of toes. We found that all toes worked significantly better across all conditions compared to hallux or lateral toes. Beyond the accuracy, we also found significantly increased task completion times for independent toe movement. Especially flexing the lateral toes made the interaction really slow. This dislike of using the toes separately is also something that we saw in the questionnaires. As you can see here, there was a much better feedback for all toes compared to hallux or lateral on the convenience of the system. So remember, independent toe movement is to be considered difficult to impossible. When we looked for the posture, we found that sitting versus standing did not have a big influence on the accuracy rates. However, we found that extension movements were significantly faster while standing compared to flexion movements. When we look at the questionnaires again, we see that extension was rated more convenient and less physically demanding compared to extension. Our explanation for this is that we need to shift our weight so we can bend our toes to flex or flex our toes downward while standing, while we can extend them, so move them upwards without any problems. So remember, while standing, give the user the option to interact with the system using extension. As the last point that I wanted to share with you is that while 4 options seems to be the only feasible option while sitting, while standing, we can have more options while sitting, where we found also comparable accuracy rates for seated interaction in flex direction with 12 targets. That's 3 times the targets, but basically no difference in the accuracy rates. So remember, while sitting, you can give the user more options through flex directions. Now, where would we use input techniques built around toe movements? One example could be private interaction in mobile settings. While riding the bus, for example, we could quickly and easily switch to the next song or adjust the volume without using our hands or using voice commands, which basically automatically would share our music selection with the people around us. Another example is situations where our hands are dirty. In this example here, we can control an application that shows cooking instructions on a display without touching it. As a last example, we think that toe-based interaction techniques are a great fit for head-mounted displays and can support input in a variety of outdoor and mobile situations. And this list is of course not conclusive. There are a lot of other use cases, for example for people with injuries or disabilities, or in other situations where traditional input devices and modalities are not accessible or practical. And with this, I want to end my talk on this totally new interaction concept. Thank you and see you in Hamburg.